Again, first step is free body diagram. We have our mg, which points towards the center of the earth. We've got our normal force, which is pointing up perpendicular to the surface. No friction on this hill, which is good. And then our force, which is pulling at 30 degrees. So doing our F equals ma equation. In the parallel direction, we have the component of the force going up the hill. So, well, let's make down the hill be positive. So we have mg sine theta is the component of gravity that's going down the hill. So that sine theta component is this one. Then we have the force component that's going up the hill, which is going to be the cosine of 30 degrees, that one. And it's not the angle of the hill, it's the angle of the rope that's being pulled right there. And that equals ma. And then in the perpendicular direction, we have normal force plus the force component that's going up here, which is the sine component. And then minus mg cosine theta is equal to ma. Because the car isn't moving, both of those accelerations are 0. In order to figure out the force that's pulling here, we're going to use this first equation, so equation 1. So that means that we have F cosine of theta, or of 30 degrees, is equal to mg sine theta. To solve for F, we're going to divide both sides by cosine of 30. And that's going to give us the force is equal to mg sine theta over cosine of 30. Our mass was 1130. 9.8 sine 25 divided by the cosine of 30. So this is the angle of the hill, this is the angle of the rope, and that gives us 5,400 newtons. To figure out the normal force, which is the second thing that they ask for, we're going to use the second equation. So normal force, if I rearrange this equation up here, normal force is going to be equal to mg cosine theta minus the force sine 30. So this is 1130 times 9.8 times the cosine of 25 minus the force we just calculated, so 5,400 times the sine of 30 degrees. And when all is said and done, that ends up being 7,300 newtons.